Welcome to the last lesson in our series on motion in one direction. In this series, we have investigated vertical projectile motion and learned how to apply equations of motion to vertical projectile motion and how to draw and interpret graphs of motion. We also investigated momentum and impulse. In the last lesson, we considered how the explosion inside a tank gun barrel caused a projectile to be ejected from the gun barrel moving in a forward direction, while the gun barrel moved in a backward direction. We were able to calculate the gun's recoil velocity because momentum is always conserved during collisions or explosions between two objects. We also calculated the force exerted on the projectile as a result of the explosion. Because impulse, which is force times change in time, is equal to the projectile's change in momentum. In this lesson, we are going to consider the energy changes that take place during an explosion or a collision between two objects. By the end of this lesson, you should be able to distinguish between elastic and inelastic collisions and describe the change in kinetic energy in a closed system. Kinetic energy is the energy that an object has as a result of its motion or movement. To calculate kinetic energy, we use the equation kinetic energy is equal to half times mass times velocity squared, where K is equal to kinetic energy measured in joule, M is equal to mass measured in kilograms, and V is velocity measured in meters per second. Kinetic energy is scalar, so it only has magnitude, not direction. When studying collisions and explosions, we need to consider the energy of the system as a whole before and after the event. In other words, we cannot just consider the gun or the projectile as two separate objects. We must consider them together. Let's calculate the kinetic energy of the gun and projectile before the explosion. The mass of the gun is 2,500 kilograms. The mass of the projectile is 34.5 kilograms. The initial velocity of the projectile and gun is 0 meters per second as they are both stationary. The total kinetic energy of the system before the explosion is equal to the initial kinetic energy of the gun plus the initial kinetic energy of the projectile. This is equal to half times the mass of the gun times the gun's initial velocity squared plus half times the mass of the projectile times the projectile's initial velocity squared. Now we substitute in the values we know. Half times 2,500 times 0 squared plus half times 34.5 times 0 squared. This gives us an answer of 0. This value makes sense as the gun and the projectile aren't moving, so they can't have any energy that is defined by motion. But what about after the explosion has taken place? Will the system have kinetic energy then? After the collision caused by the explosion, the masses of the gun and the projectile haven't changed. The projectile is moving at 1,575 meters per second. And the gun is moving at 21.74 meters per second. So the total kinetic energy after the explosion is equal to the final kinetic energy of the gun plus the final kinetic energy of the projectile, which is equal to a half times the mass of the gun times the final velocity of the gun squared plus a half times the mass of the projectile times the final velocity of the projectile squared. When we substitute in what we know from our list, we have a half times 2,500 times 21.74 squared plus a half times 34.5 times 1,575 squared. This gives us 5.91 times 10 to the 5 plus 4.28 times 10 to the 7. The total kinetic energy after the explosion is 4.34 times 10 to the 7 joule. The initial kinetic energy of this system was 0, so we can see very clearly that the kinetic energy before the explosion is not equal to the kinetic energy after the collision. The explosion is described as being inelastic. The kinetic energy of the system has not been conserved. The projectile and gun had no kinetic energy before the explosion, but afterwards they were both moving. Where did this kinetic energy come from? The explosion caused by the firing pin hitting the shell released gases, which exerted an external force on the projectile, moving it forwards. Remember that momentum needs to be conserved. So as the projectile moves forwards, the gun barrel moves backwards. This motion means that the gun barrel now also has kinetic energy. The objects gain kinetic energy from the external forces applied on the projectile. What do you think happens when the projectile finally hits a target? Once again, we will see that kinetic energy is not conserved, so the collision is inelastic. Notice how the metal box changes shape as the projectile moves through it. This means that kinetic energy is not conserved because the metal changes shape. It is deformed, which requires an external force. Sometimes the projectile itself will change shape or be deformed. We can do a calculation to prove that the collision between the metal box and the projectile is inelastic. As the projectile approaches the box, it is traveling at 1,575 meters per second. The box, however, is stationary. The box has a mass of 200 kilograms and the projectile's mass is 34.5 kilograms. After the projectile has passed through the box moves at 50 meters per second in the projectile's original direction. Where should we begin in order to show that the collision is inelastic? First, we need to know how fast the projectile is moving after passing through the box. The law of conservation of momentum will solve the first part. Before colliding with the box, the projectile had a mass of 34.5 kilograms and an initial velocity of 1,575 meters per second. We also know that the box had a mass of 200 kilograms and was stationary before the projectile collided with it. After the projectile moved through the box moved at 50 meters per second. We need to work out the velocity of the projectile. Let's apply the law of conservation of momentum to calculate the velocity of the projectile. Total momentum before the collision is equal to the total momentum after the collision. So the mass of the projectile times its initial velocity plus the mass of the box times its initial velocity is equal to the mass of the projectile times its final velocity plus the mass of the box times its final velocity. Substitute in the information we know. 34.5 times 1,575 plus 200 times 0 is equal to 34.5 times the projectile's final velocity plus 200 times 50. Therefore, 54,337.5 plus 0 is equal to 34.5 times the projectile's final velocity plus 10,000. So 34.5 times the projectile's final velocity is equal to 44,337.5. Lastly, solving for the projectile's final velocity, we see that it is equal to 1,285.14 meters per second. We now have enough information to calculate the kinetic energy of the system before and after the collision. It's important to remember that the before and after calculations must be done separately. We'll begin with the total kinetic energy of the system before the projectile went through the box. The total kinetic energy before the projectile went through the box is equal to half times the mass of the projectile times the initial velocity of the projectile squared plus half times the mass of the box times its initial velocity squared. Substituting in the information we know, we have a half times 34,5 times 1,575 squared plus a half times 200 times 0 squared. So the total kinetic energy before is equal to 4,28 times 10 to the power of 7 joule. Now we work out the total kinetic energy after the projectile has moved through the box. The total kinetic energy after is equal to a half times the projectile's mass times its final velocity squared plus a half times the mass of the box times its final velocity squared. Substituting in the values we know about the box and the projectiles after the collision, we have a half times 34,5 times 1,285,14 squared plus a half times 200 times 50 squared. This gives us 2,85 times 10 to the power of 7 plus 2,50 times 10 to the power of 5. The total kinetic energy of the system after the collision is equal to 2,88 times 10 to the power of 7 joule. Let's compare the kinetic energy of the system before and after the collision. So it is clear that the kinetic energy of the system changed as the projectile moved through the box. In fact, we see that the total kinetic energy after the collision is less than the kinetic energy before the collision. We know from the law of conservation of energy that energy cannot be lost, but is transformed into other forms. Where does the kinetic energy go? As the projectile moves through the metal box, it makes a loud noise. Kinetic energy is transformed into sound energy. Secondly, as the projectile moves through the metal box, the box gets hot. This is caused by the friction of the projectile scraping against the metal. Kinetic energy is also transformed into heat energy. Sometimes it is possible for the kinetic energy to be transformed into light during an inelastic collision. Tank gun ammunition going through metal boxes is not an everyday occurrence, is it? But every day on our roads, there are numerous inelastic collisions. For instance, when two cars collide, the momentum of the system will always be conserved, but the kinetic energy will not be conserved. Modern cars are designed to crumple on impact, so they deform. This is deformation energy, which comes from the original kinetic energy of the cars. Also, car accidents usually result in a lot of noise, so kinetic energy has been transformed into sound energy. Now, while some collisions are inelastic, others are elastic. Can you work out what this means? You see, in an elastic collision, kinetic energy is conserved, but this can only happen if there is no friction or any other external force present. Elastic collisions don't transform energy to sound or heat, so actually there are very few elastic collisions in everyday situations.
Hi everybody, I'll need a very smooth surface to prevent friction and these two shiny balls which also offer very little resistance. Watch what happens as the two balls move towards each other. Both balls have a mass of 150 grams. Ball 1 is traveling at a speed of 2 meters per second and ball 2 is traveling at a speed of 1,5 meters per second. They collide head-on. After the collision, ball 1 travels at 1,5 meters per second to the left. With this information, you should be able to calculate the velocity of ball 2 after the collision, and then work out if the collision is elastic. It's been a pleasure. Goodbye.
Let's work out the velocity. To start, take any motion to the left as positive. we know that the mass of both the balls is the same, which is 150 grams. We convert this to kilograms, so they have a mass of 0.15 kilograms. Ball 1's original velocity was 2 meters per second, and ball 2's original velocity was negative 1.5 meters per second. It is negative because ball 2 was moving to the right. Ball 1's final velocity was negative 1.5 meters per second. What will the final velocity of ball 2 be? To find the final velocity of ball 2, we use the law of conservation of momentum. The total momentum before the collision is equal to the total momentum after the collision. Ball 1's mass times its initial velocity plus ball 2's mass times its initial velocity is equal to ball 1's mass times its final velocity plus ball 2's mass times its final velocity. We substitute in all the values for mass and velocity. So 0.15 times 2 plus 0.15 times negative 1.5 is equal to 0.15 times negative 1.5 plus 0.15 times the final velocity of ball 2. This gives us 0.3 minus 0.225 equal to negative 0.225 plus 0.15 times ball 2's final velocity. Or, when adding 0.225 to both sides, we can say that 0.3 equals 0.15 times ball 2's final velocity. After solving for ball 2's final velocity, we find that it is equal to 2 meters per second to the left. The answer is positive, so the ball is traveling to the left.
We also have to show, using the appropriate calculations, that the collision is elastic. Remember, to prove that a collision is elastic, we need to calculate the total kinetic energy of the system before the collision and the total kinetic energy of the system after the collision. If the collision is elastic, then the kinetic energy before will be equal to kinetic energy after the collision. The total kinetic energy before the collision is equal to a half times ball 1's mass times its initial velocity squared plus a half times ball 2's mass times its final velocity squared.
This means that we have a half times 0.15 times 2 squared plus a half times 0.15 times negative 1.5 squared. This gives total kinetic energy before the collision of 0.47 joule. Let's keep this value in mind. Kinetic energy before the collision is 0.47 joule. The total kinetic energy after the collision is equal to a half times ball 1's mass times its final velocity squared plus a half times ball 2's mass times ball 2's final velocity squared. Therefore, we have a half times 0.15 times negative 1.5 squared plus a half times 0.15 times 2 squared. Doing the maths, 0.17 plus 0.3. So the kinetic energy after the collision is 0.47 joule. We have proved that the total kinetic energy before the collision is equal to the kinetic energy after the collision. Thus, the collision is an elastic collision. To revise what we have learnt this lesson, an inelastic collision is a collision in which kinetic energy is not conserved. So the total kinetic energy before the collision is not equal to the total kinetic energy after the collision. An elastic collision is a collision in which kinetic energy is conserved. So the total kinetic energy before the collision is equal to the total kinetic energy after the collision. Now for this lesson's task, We'll continue the task from the previous lesson looking at kinetic energy. A truck with a mass of 4,500 kilograms traveling at 20 meters per second hits a car from behind. The car with a mass of 1,000 kilograms was traveling at 15 meters per second. The two vehicles now connected carry on moving in the same direction. Question 1. Determine the kinetic energy of the system before and after the collision. Question 2. Is this an example of an elastic or inelastic collision? Give a reason for your answer.